So, I am going to start a case study where we are going to take a typical transmission system. So, let us take our 100 gig transmission system and the symbol rate is 25 gigabaud, 25 into 10 power 9. Let us say we are trying to analyze now 2 power 14 symbols would mean this would be about 16384 symbols, and that would correspond to multiplied by 2 bits in case of QPSK, multiplied by 4 in case of 16 QAM. Let us stick to QPSK, and the reason for choosing these number of bits is because you need to be able to arrive at a very reliable number for bit rate, statistically reliable number for bit error rate, and if you say that I can safely say that the bit error rate is statistically correct if I have detected, let us say, 10 bits in this 16384 into 2, this many number of bits, the allowed bit error rate for assuming this statistics is about 3 into 10 power minus 4. So, the choice of number of symbols is simply decided by the reliability of the bit error rate that we are estimating. So, let us say that if we detect 10 bits in this whole bit sequence as error bits, it means that 10 divided by these number of bits is roughly around 3 into 10 power minus 4. It means that the calculations that I am doing, I can reliably determine bit error rate for a number up to 3 into 10 power minus 4. That is what it means. Okay. And so, I have my symbol, and the symbol duration is about 40 picoseconds because I have chosen 25 gigabaud as my symbol rate. And let us say that each symbol is denoted by 10 sample points. Okay. I have 10 samples that represents the symbol, and the symbols I am generating through the bits that I am generating are through random bits. So, I am using a PRBS order of 9, and I am using QPSK configuration. So, the number of bits per symbol is 2. Some other simulation parameters I am using are the line width of the laser. I mean, I can keep changing this number, the input power, input wavelength, the local oscillator power. So, the frequency detuning between the signal frequency and the local oscillator frequency. Some of the fiber parameters also needs to be defined. So, speed of light in vacuum, Planck's constant, dispersion coefficient, this should be plus 17 picosecond per kilometer nanometer. Fiber length, I have chosen 80 kilometer for these simulations. Optical signal to noise ratio is a variable, alpha is 0.2. So, these are some simulation parameters that we are setting aside for the entire discussion. Okay. And remember, needless to say, we are running writing a MATLAB code, or it could be in Python or C or anything. Since we are doing this digital signal processing, we are dealing with discrete time sequences. How do you generate the QPSK modulation? Of course, you use the standard MATLAB function. So, you generate the PRBS bits, and then I have to generate a QPSK configuration. So, that is what these functions are doing, right. So, this is bit to decimal conversion. You have so you first generate 512 bits corresponding to I data. This is the repeat for Q data, and you reshaped it so that you have an I and Q arranged in a matrix, and then the data is actually generated through this function, again QAM modulation function of MATLAB. Now, this step looks at resampling. We already said that there are 10 samples per symbol. So, this function actually does the resampling and gives you 10 samples per signal, and from there you are generating your I signal and your Q signal. Now, how do you generate your optical carrier? The number of FFT points is the length of your signal. Your symbol duration is 1 by symbol rate. So, these are some of the variables that you are defining. Your symbol duration is 1 over symbol rate. So, your d tau is the spacing between two adjacent samples. So, you said that you are going to pick 10 samples to represent the symbol. So, you have d tau is t symbol divided by nt. we now need to do phase noise generation and frequency offset generation. We will come to that in detail later, but in the end you want to multiply the power with ECW is square root of power multiplied with, so you are going to have square root of P in e power j phi n, and this phi n is the phase noise. I will tell you later how to do the phase noise generation. Once you generated the carrier, then the next process is to do the IQ modulation. We have already seen the structure of the IQ modulation. So, it has two child Mach Zehnder interferometers and a big arranged in a big Mach Zehnder interferometer. So, the Mach Zehnder modulator you need to feed in the in phase and the quadrature data. So, this is the electric field that generates the in phase component, and this is function represents the function of the top Mach Zehnder modulator, and it is biased in the push pull configuration. So, you have a V1 and you have a minus V1 which is fed on the two arms of the push pull Mach Zehnder modulator. So, that is what is represented here, exponential j pi, this is your signal. So, this is of the form exponential j pi v of your divided by 2 v pi. 2 v pi indicates that it is in the push pull configuration, and plus of course you have two fields coming in. So, this is the top field here and this is the field coming in from here, and because your I signal is negative here, you have a negative corresponding to this negative V1, and similarly the bottom arm, and later you combine them after a phase modulator. So, you have E out is E1 plus pi by 2 introduced by the phase modulator and E2 here. Now, if you want to model IQ imbalance in the system, of course, you need to add a theta there. In the coherent receiver, of course, we have discussed in detail. You have two balanced photodiodes, and so you have I1, I2, I3 and I4. We had derived the electric fields in detail for each one of them. So, these are the 4 electric fields after you get the hybrid, and the photodiode current is actually the real part of the electric field times its conjugate. And you also need to add noise to each of these photodiodes. So, again in receivers you have learnt about the short noise and the thermal noise. Of course, you are using a coherent receiver, so the thermal noise is going to be much smaller than the short noise, but just for the sake of completion you have added the short noise here, and this is the thermal noise of the system. So, the total receiver current is actually having all these 4 components, which is the total the current plus the noise in each of these arms. Now, you form the complex signals. So, what you do at the output of the coherent receiver is the first one minus the second one, the third output minus the fourth output. We had already discussed this before. So, you construct your complex signal from your in phase and quadrature component. You could do this separately for X polarization and Y polarization in case of a polarization and phase diverse coherent receiver. So, the first impairment we are trying to correct for is the frequency offset. Okay. Now, the output of the coherent receiver, the I1 minus I2 and I4 minus I3, right. So, that component has the phase of the signal that you want to extract, but it also has the IF frequency, and this IF frequency is the frequency separation between the signal laser and the local oscillator laser, and this is the frequency offset that we are talking about. So, let us say the signal laser is at frequency FRX and the local oscillator is at a frequency FTX, and these are two different lasers, because the signal laser is, the transmitter is kept at one transponder, the receiver is in another transponder, and even though you can tune the lasers very close to each other, it is very hard to make them synchronous, the frequency, to adjust the frequency of the laser synchronously. So, there is always a frequency offset in the system, and this frequency offset, what is the consequence of having the frequency offset? It will keep adding a phase in every symbol point, and that phase is quantified by 2 pi times the frequency times the time, because that is a phase accumulated in every as a function of time. So, if your Ts is your symbol duration, right, as you progress in time, for the nth symbol, you will have the phase accumulated from all the previous n symbols. So, this is like a cumulative effect, and of course, FD is the frequency difference between the transmitter laser and the receiver laser. Okay. So, the consequence of this is that you would have started with a symbol, let us say 1i plus 1j. As time progresses, the phase of the resultant beat signal keeps progressing. That is what it means, right? And with the result that the entire constellation will now form a circle. So, let us take an example of frequency offset. Let us say the frequency offset is 100 megahertz, which is still a very small number. This 2 pi in over one symbol, it simply means that the resultant phase, this is the undesired phase. Okay. This resultant phase, because of this omega IFT, that would have accumulated by 2 pi times FD times Ts in one symbol duration, and this is about 0.025 radians, which means that over let us say 2 power 14 symbols is our situation. Over 2 power 14 symbols, it would actually, if you calculate, it will accumulate about 411 radians, which means that there is an additional phase in the system which keeps progressively increasing with time, and that results in the constellation being rotated. Okay. So, this is an impairment that needs to be corrected, but the good thing is that you can potentially find out what is the frequency offset, and you can progressively keep decreasing the phase. So, if after one symbol there is a 0.025 radians, if only we are able to find out what this FD is, after every symbol from my answer, whatever phase I estimated, I will kind of subtract this number and bring my constellation back to the same point. Okay. So, first of all, we will see how to generate this laser, the frequency offset, and then we will try to see how to correct for it. So, in order to generate, it is very simple. This is the minimum frequency in my simulation, that is decided by my d tau, the smallest time spacing between the sampling points. So, let us say total time window is t, and I have d tau as the spacing between the two adjacent sampling points, and I have NFFT number of points here. Then it means that the frequency minimum is 1 by d tau times the NFFT, which is also the same as symbol rate divided by the number of symbols that I have chosen. And so, the minimum, so F minimum is, so these steps are to make sure that the frequency offset that we want to simulate is complying to the discretization, the time and the frequency discretization that we have chosen. So, we had defined a specific detuning between the LO and the signal laser. So, you can calculate what is the detuning in each step, and you can progressively keep multiplying that detuning phase into to the signal to the LO field, and that will emulate the phase accumulation in each time step. Now, how do you do the correction? So, let us say in the absence of all the other impairments, the received signal can be modeled as R of t is equal to e power j 2 pi f d. This is because of the frequency offset. SL is of course my symbol, and P times t minus L T s is simply my shaping function for my, it could be for, so for example, in a RRC shaped pulse, or for a NRZ shaped pulse is just a square function, right. So, the objective is I need to extract this FD. So, what we do is we take the Fourier transform of the fourth power of the signals. So, this is what happens when you take the Fourier transform of the fourth power of the signal. Fourth power of the signal is multiplication by 4 times in the time domain, which means that you are doing successive convolution 4 times in the frequency domain. So, which means that in the frequency domain you are going to get a specific signature at your 4 times the frequency offset. Now, the fourth power is done to ensure that this exponential does not result in this zero sum, okay. And this Fourier transform becomes maximum when f is equal to 4D. So, the algorithm is very simple. So, this is representing the Fourier transform. If you do a fourth power of your received sequence and do a Fourier transform of this, you get a peak corresponding to 4 times FD. So, the algorithm for frequency offset correction is quite simple. SL is the message. First you raise the signal to the fourth power, then you do a Fourier transform, find out the spectral peak at 4D, from that obviously you can find out D, and then you remove the progressive phase rotation, which means you are doing a multiplication e power minus j 2 pi FD times NTS for the nth sample. The good thing is this is modulation format independent. You never use the fact that this is a QPSK modulation or 16 QAM modulation. So, this idea works for any modulation format. So, this is how it is going to look like. So, let us look at the code. So, you are raising to the power 4, this is your input data. So, the frequency offset error is first of all you can subtract the mean and you can take the FFT, take the absolute value and then you find out the maximum. So, that maximum will correspond to 4 times D. So, you are doing 1 divided by 4 of this maximum and then you estimate the Hertz error in frequency offset, and then in the received sample you are just multiplying it by minus 2 pi frequency offset estimate times, of course, progressively you keep multiplying in every sample. Okay. So, you get, this is how you compensate for frequency offset. The question next we are asking is what is the largest value of frequency offset that can be corrected? Can you correct any frequency offset between any value of frequency offset between the transmitter laser and the LO laser? And the answer is very simple to see that if I have my sampling frequency as Fs, the largest frequency that I can determine is Fs by 2. That is decided by my Nyquist. Now, when you do the fourth power, you are convolving 4 times. It means that it is as if the frequency axis is now expanding by 4 times, which means the largest frequency that you can determine is actually scaling by 4, which means that the largest frequency offset that is detectable is only Fs by 8. Or so long as your frequency offset and the sampling are such that this condition is satisfied, you can always compensate for any frequency offset between the transmit laser and the received laser. This is of course how the constellation looks like just after frequency offset correction. The next issue is phase noise of the laser. So, this we have seen when we were talking about lasers, that a practical laser will always have a finite line width, and this reason for this line width are multiple. We have seen how to quantify the line width through the line width enhancement factor and so on. The problem with line width is that it adds unnecessary phase fluctuations. So, in case of a QPSK constellation, for instance, the line width basically results in the rotation of the constellation. And how do you know how much rotation is allowed? So, that is decided by what is called as a phase margin. Phase margin is the minimum angle between the closest constellation points, right. So, in case of QPSK constellation, the phase margin is 45 degree, whereas in case of 16 QAM constellation it is 16.9 degree, which means that the line width that is tolerated for QPSK constellation may not be tolerated for 16 QAM constellation. So, how does one model the line width? We have seen this in the laser module before, but just as a quick recap, it is modeled as a random walk process, which means that for every symbol k, if I am talking about the kth symbol, the phase of every symbol gets added by this number, which is summation 0 to k phi I, where phi I is a IID random variable. It is a Gaussian random variable with 0 mean, and the variance of this random variable is decided by your line width and the symbol duration. So, for a symbol duration of 40 picoseconds, right, for a frequency delta f of let us say 100 kilohertz, you can calculate what is the variance of the random variable that needs to get generated. So, you generate that random variable, And then what you need to do is that for every symbol, right. So, this is let us say kth symbol. So, you have the random variables generated from I is equal to 0, 1, 2, 3 etc. The phase that gets added for the kth symbol because of the phase noise is actually the sum of the phases, where this phi I is the phi naught, phi 1, phi 2 etc. are picked from that Gaussian random variable set, okay, which has a variance decided by this. So, this is how you generate the phase noise. So, this is what you do. First of all, you generate the find the variance of the random variable that you need to generate. So, this is where you are doing that. So, first this is the random variable generation, and here is where the variance of the due to the line width is generated, and you created the phase noise vector by multiplying this phi naught with the random variable, right. And the phase noise for any specific symbol is the cumulative sum of the phase accumulated up to that point. And so, your electric field is ECW, which is square root of power. So, electric field is square root of P in times exponential j times phase noise, and this phase noise for the kth symbol is the summation from cumulative sum from the previous phase noise accumulated from the previous symbols, okay. And this is an example for a CW case. If you do this generation for 10 kilohertz, you will have an arc like this. For 100 kilohertz, the arc is like this, right. So, since the spread is known, we can now try to see how to design a filter that is going to compensate for this phase noise. So, the filter that we are looking at is a decision directed LMS filter. It is a single tap adaptive filter. So, what does it mean? Let us assume that x of n is the received data, and in the whole discussion we are assuming that there is no other impairment, it is only the phase noise that is affecting my received signal. So, let us say x of n is my received signal. If only I knew what my theta rotation is for that specific signal, I could have generated my output y of n as simply y of n is equal to x of n times w of n, where w of n is e power minus j theta n ideally, where theta n is that cumulative sum that I added. But the point is, in reality we do not know what that cumulative sum is, because it is a statistically varying quantity. Okay. So, even if we know what the line width is, it is not really possible to estimate what exactly the phase gets added at each location. So, what do? You model this system as a single tap adaptive filter, which means that the impulse response of this adaptive filter, let us call this as W, which is also called as the weight of the filter. What you do is initialize that weight as initially as 1. You assume that the phase noise added is 0, so the weight is 1 to start with, and at any instant n you compute yn is wn into xn, right, and then you compute the error, right. Now, error at time instant, so this is again n, the error at time instant n is E of n is d of n minus y of n. Now, this d of n is the decision that you have taken, right, and that decision is depending on whether you are in the training mode or in a tracking mode, this decision could be different. For example, you can run this algorithm in a training mode, in the sense that you already tell the receiver that okay, these are the bits that I transmitted. So, this error is calculated with respect to what are the bits that I transmitted. So, for instance, I could say that the first bit that I transmitted is actually, or the first symbol that I transmitted is actually 1 1, then my y of n, my E of n is actually 1 1 minus whatever I received during that instant of time, okay, if I know what is a transmitted bit. Then what I do is, I do an update of this filter coefficient through LMS equation. And what is that stochastic gradient update equation? Of course, these are the concepts that you would learn in detail in digital signal processing, but we are just borrowing the results from there right now. So, the filter update is based on minimizing the okay, minimizing the between the previous value and the next value. So, this is the filter update equation. So, from that update equation I again go back to, after I updated my filter value, I go back to my next step. I keep doing this again and again. Okay. So, I do this for all the symbols, all the time instances, and at every time I am trying to compare my received signal with, in the training phase I try to compare with the symbol that I transmitted, but you cannot always know, the receiver cannot always know what the symbol is transmitted, then there is no need for communication system, right. So, you have to get out of the training phase and then you move to what is called as tracking phase, and in the tracking phase what you do is you compare only with the ideal constellation point. So, this D of n could be the nearest closest ideal constellation point. So, suppose this is my received signal, I compare with my the distance from my ideal constellation point, and that is my, that defines my E of n. So, this is how the algorithm works. So, as I said earlier, in the training mode, this error in the nth iteration is the training symbol minus my received symbol. Once the training phase is over, once the algorithm is stable, you can get it into the tracking mode, where now you can start comparing the received signal with the nearest constellation point, right. So, you do it with do the error, you calculate the error with using D of n, where D of n is a symbol in the constellation which is very close to the received symbol. So, this is how the algorithm works. So, the MATLAB implementation is what is shown here. So, you have some parameters called as the step size of the filter, which is characteristic of any adaptive filter, and of course, the weight of the filter. So, the step size is chosen to be this, the initial value of the weight is chosen to be 1, and every time you compute the error and you update your weight and you keep repeating this until you reach the end of the symbol. Okay. So, you keep, so what you will see is that progressively the filter weight keeps updated. Initially first few symbols you may end up with error, but progressively the filter weight gets updated and you will end up correcting for phase noise of every symbol until the end of your sequence.